Hello and welcome back to this online course on fundamentals of composites and cellular materials. So, today's plan is to discuss the remaining ceramic matrix composite synthesis techniques, and then we will get involved in synthesis of polymer matrix composites. So, let us start. In the last class, as if you remember, I discussed about the different ceramic matrix composites synthesis techniques, and today also we will talk about a couple of more techniques, and then we will talk about applications, and then we will jump into polymers, that means polymer matrix composites. So, in today's class I plan to discuss sol gel technique and electrophoretic deposition. Okay. How these methods are not new methods, sol gel technique or EPD are not new methods, but this actually can be used to make ceramic matrix composites. I have talked already about sol gel technique. Let us see how sol gel technique can be used here as to make CMC. So, if you remember, as I talked about sol gel technique, in sol gel technique basically there will be a solution, okay, and in that solution there will be fine particles making the emulsion, okay, and this emulsion, okay, emulsion, or basically it can call also colloidal solution, okay, and this called sol, and these particles are, as I mentioned earlier, are basically alkoxides. This precursor material is alkoxide. Now, by sol gel technique we can only synthesize, or we can get the oxide material. Okay. So, alkoxides are used as the precursor material that makes the sol, and this sol goes through hydrolysis and polycondensation. And that leads to formation of gel. Okay. Gel means basically a viscous material with network, and this gel at higher temperature basically gets calcined, or calcination is done, okay, and then ultimately you get the oxide material. So, the same process is done here, but when you are doing it, so the idea here is that this oxide will be the matrix. So, what you do in this solution, it is not only the alkoxide being added, but also the ceramic particles will be added here, which will be acting as reinforcement. So, now you are adding, along with alkoxide, you are adding reinforcement. Okay. So, you can have particles or short fibers. So, that is what you see here. The basically an example has been shown here. So, you can see here alumina matrix, which is reinforced with this lanthanum hexaaluminate. Okay. So, this alumina has been prepared or synthesized by sol gel technique. That is the basic process of sol gel technique by which ceramic matrix composite could be synthesized. Just to recapitulate, you make the sol of the alkoxide. In that sol you also add the reinforcement particles or short fibers, and then you go through the process of sol gel technique. By that technique you get the oxide matrix, and this oxide matrix, the particles or fibers which were used as, which were which is supposed to be the reinforcement, those gets nicely distributed. That is the basic technique of sol gel technique. Now, obviously advantage means it is a low temperature process, there is good control of you can see lower processing temperature, good greater compositional homogeneity, true. Okay. Ability to produce multi-phase matrix material, you can have multi-phase matrix, that means by Sol-Gel technique we can have mixed oxide of SiO2 and Al2O3. So, there is a multi-phase matrix, okay, which is not possible always. Okay. So, multi-phase matrix along with reinforcement, and disadvantages certainly shrinkage is a problem, low yield, process is slower, okay. You get a very small amount of material after doing all these things, okay. Requires repeated impregnation for producing dense material, that means you have to do Sol-Gel technique, you have to keep on doing it actually, okay. So, once the oxide matrix is made, again you fill that, try to fill that with Sol and go through the same process, okay. So, that means the process, it does not give good densification in one go, okay. So, let us now move on. The next process is EPD, electrophoretic deposition. Again, electrophoretic deposition technique is a not new technique. What it says based on the movement of deposition and deposition of charged particles, movement and deposition of charged particles under electric field onto a conductive electrode to develop thin film and coatings. Okay. Now, just to show you what exactly is that method, again I would like to draw it quickly for your understanding. So, you have this electrolyte obviously, and then electrolyte is there. So, let us say this is the chamber where you have the electrolyte, okay, and you have anode and cathode, okay, anode positive, cathode negative, and then what happens, you have these charged particles. So, the very small particles, nanoscale particles are distributed, I mean basically it makes a colloidal solution in the electrolyte, and these nanoscale particles, because of this application of the voltage, gets charged, okay, and these charged particles goes to the cathode and gets deposited there. That is the basic technique of electrophoretic deposition. Now, the idea is that this cathode, let us replace that cathode with a preform. So, now I have a fiber preform, basically that is the cathode, okay, and do the same thing. So, now and in this here the particles which are distributed in the electrolyte, these particles are nothing but what? The ceramic particles, the ceramic matrix particles, okay, ceramic matrix particles. Okay. So, now you are doing the electrophoretic deposition technique. So, this gets charged, okay, and let us say they get negatively charged, sorry, in this case positively charged because it goes to a cathode. Okay. So, this moves on and gets deposited in the preform, inside the preform, okay, and that is the simplest way of electrophoretic deposition technique by which you can make a ceramic matrix with reinforcement. Let us see what do we have in our slides, and you see it says that simple and inexpensive technique can be used to infiltrate tightly woven preform, okay, nanoscale ceramic particles which basically forms a stable non-agglomerated form such as in a sol or colloidal suspension. So, as I mentioned earlier, in the electrolyte these nanoscale particles are distributed as sols, like makes a colloidal solution, and then application of an electric field that actually so the particles, the nanoparticles gets surface charged, that means the surface gets charged and they gets carried to the electrodes with migrate and deposit on an electrode. Okay. By replacing the electrode with the conducting fibrous preform. So, now the electrode is replaced with the preform and that gives you the whole thing. How do you make it conduct the preform? Okay. You can think about having lot of different kind of coatings like carbon coating or gold coating just to make it conductive. and then the and this carbon coating thin film coating will be like few nanometric layers. So, it does not matter that much. So, that is the process, and as you can see here it has been shown nicely. You have these anodes, okay, and then this cathode is basically the preform, and then because of the application of the electric field, the charged particles goes into the fiber preform and it fills it and it gets densified. An example you can see, nice example you can see here. Here this spherical things are basically the nickelon fiber, and this matrix which actually gets densified around the fiber preform, the nickelon preform, is in this case mullite. Mullite is basically a mixed oxide of SiO2 and Al2O3. Okay. So, that is electrophoretic deposition. So, with that, now I have ended talking about synthesis of ceramic matrix composites, and applications I have talked about earlier also. Now also you can see here, starting from electronic to automotive to aerospace, defense, medical, industrial, everywhere there are applications of CMCs, ceramic matrix composites, especially where high temperature applications are there. Ceramic matrix composites are now inevitable. Okay. Some more examples, these are actually different tools, tool geometry which are made by cemented carbide. Okay. So, in this case here actually this is silicon carbide whiskers reinforced alumina composites are used as cutting tools, inserts for high speed cutting. Here also you can see here filter, candle type filter, which is reinforced with alumina fiber. Nextel is nothing but alumina fiber in a silicon carbide matrix, okay, and that is used actually at 1000 degrees Celsius, okay, to remove particulate matters. So, these are basically some filters, candle type filters. Similarly, in aerospace applications, okay, a very nice example actually you can see here. It says that a LEAP engine, the first commercial jet engine to use CMC, silicon carbide fiber with silicon carbide matrix. So, this is actually the CMC shroud. You can see the shrouds are shown here, and the cross section of the shrouds are shown here. So, this is actually done by General Electric, and for the first time CMCs have been used in this kind of high pressure part in turbines. Again, there are multiple examples of ceramics. We can go ceramic composites, we can go on for a long time, but now let us move to a new topic which I already told that I will be talking, is polymer matrix composites and their synthesis. So, polymer matrix composites are basically classified in two groups: reinforced plastics. Okay, we all know about reinforced plastics. These are also called GRP. That means glass reinforced plastics. Okay. So, these are actually, you do not really need very high strength, you need fairly high strength, like boat hulls, okay, like in some cases windmill panels. Okay. So, where you need good amount of strength, but not extremely high strength. So, these are made by this kind of, and you need also lightweight. In those cases these GRPs are used, typically consist of polyester resin reinforced with low stiffness glass fiber. And then you have advanced composites, okay, which are reinforced with high strength fibers like carbon or boron fibers, okay, sometimes ceramic fibers as well like SiC and Al2O3, and these are primarily used in aerospace industries where you need superior strength and stiffness. Okay. So, that is basically about the classification of polymer matrix composites in terms of their applications. Now, let us quickly discuss on the classification in terms of polymers. Okay. So, obviously, we have two different kinds of polymers, one is thermoset, other one is thermoplastic, and accordingly we have two classes of composite materials based on what kind of polymer matrix is that. Now, key attributes of polymer matrix composites is that its strength is not that high, it cannot really compare with MMC or CMC, but then specific strength is extremely high. What do you mean by specific strength? Strength over density. When you compare with density, specific strength of polymer matrix composites are enormously high because of the reinforcement. Okay. Similarly, high specific stiffness, and because of the reinforcement again abrasion resistance increases, okay. Abrasion resistance, impact resistance increases, and polymers are by nature generally not thermally and electrically conductive or bad conductors of heat and electricity, but then you can reinforce with certain materials, and that could lead to improvement in the thermal and electrical conductivity. Obviously, most of the polymers are good corrosion resistance, and ultimately the final thing is that it is low weight, definitely the cost is also low. Okay. So, there are a lot of different applications where CMCs are used, but you cannot use them in high temperatures because of their low thermal resistance and high coefficient of thermal expansion. So, now let us discuss few techniques each for thermoset matrix composites and thermoplastic matrix composites, that how we can synthesize these different kind of polymer matrix composites. Okay. So, you can see here there are different techniques have been mentioned here, and definitely I will not discuss all of them, but the salient ones I will discuss quickly for your information. So, the first one you can see here. So, let us go first talk about thermosets, and in thermoset matrix composites the first one says hand layup and spray technique. This is the most primitive one and still being done, okay, which is this particular one, hand layup and spray technique. So, what is done here basically? So, you can see here in this cavity, first in case of the hand layup, first these fibers are laid down. Okay. So, fiber mats or fiber, short fibers, continuous fibers, whatever fibers you are required, those are laid up in this, laid onto on this mold, and then the resin is poured, the thermoset resin is poured, okay. And then hand roller is used to, when it is getting densified, the resin is getting densified, I mean resin is getting solidified, then in that process this hand roller is used to even make it more densified. Okay. So, that is the process of hand layup. You get thermoset matrix along with the fibers being distributed. Similarly, it is almost similar, this spray technique is almost similar. In this case, you are not using hand or this kind of pouring, but spraying both the resin and the, what do you call it, this chopped fibers or short fibers. Those are all sprayed together. Okay, you can see here. Okay. So, this is the continuous strand rubbing also can be actually sprayed here, okay, or you can see here the, okay, this continuous strand is going there like this, and then there is a chopper. This basically makes short fibers, and the short fibers gets distributed, gets thrown along with the resin, and then it again you use a hand roller to make it densified. So, that is the basic technique, a very primitive technique of making ceramic matrix composite. The next one is filament winding, lot of application of this. It is extremely famous to make cylinders, to make pipes, okay, GRP pipes, glass reinforced pipes, okay, glass reinforced polymer plastic pipes, okay, storage tanks, huge big storage tanks where temperature is not a factor, okay. Those kind of tubes or those kind of cylinders are being made by this filament winding. What is done here? So, you can see here there is a mandrel, and this mandrel is having the profile of the cylinder or the tube what you want to make ultimately. So, this mandrel, what is the application, what is being done here? So, you can see here this is resin impregnated fiber. So, a series of fiber goes through a resin pool and gets impregnated by that resin, right, and then it moves through this particular machine, so that then all comes together, the resin impregnated fibers come together and then gets winded in this mandrel. As you can see here, there could be different kind of winding. Okay, you can have helical windings, you can have hoop windings. you can have different designs of windings. Multiple winding takes place like this, and then ultimately once it gets solidified, once the resin gets solidified, then this mandrel gets removed. So, then you have a hollow cylinder or a hollow tube or hollow pipe, okay, which is made of this, and these fibers are generally glass fibers. It could be other fibers also like Kevlar fibers, okay. But ultimately you get this kind of cylindrical structures or pipe structures, and that is the process of filament winding. So, you can go through these texts and you can get the information, but that is the basic process of filament winding. The next one is again a very well used method, pultrusion. Okay. In pultrusion you get sections like this. So, you get polymer matrix composites, sectional polymer matrix composites, long sectional polymer matrix composites by this method. So, what is done here? There will be krills of fibers, different fibers. Okay. So, in the fibers, in the krills we have the different fibers being rolled, and then this krills goes through a guide, and then ultimately it goes through a resin bath, gets impregnated, that means it takes away the resin along with it, and there will be this kind of sizing treatments, so which basically wipes away the extra amount of resin, and then finally it goes through a dye, and it gets, in that dye it gets cured, okay. And the dye could be having different kind of shape, like this kind of sections or whatever, and then ultimately you can see there is a cut off. So, that means at different length the continuously casted, continuously made this kind of sections, the length get cut, okay. So, that is the basic technique of pultrusion. Pultrusion says continuous sections of polymer matrix composites with fibers oriented mainly axially are produced. So, you can see here it is a continuous sections of polymer matrix being reinforced with continuous fibers, okay. Continuous fiber toes come from various krills, are passed through a resin bath. The resin impregnated fibers pass through a series of wipers to remove excess polymer. The resin is cured in the dye and the composite is pulled out, okay. So, in the dye the resin gets cured, and then the composite material gets pulled out from the dye, and that is how you get this kind of sections, okay. Obviously, in all cases you can see the labor cost is low, product is consistent, okay, and common resins are polyester, vinyl ester, epoxy and other. Okay. So, this is the basic process of pultrusion. So, I have talked about 3 techniques so far, and these all are used, by the way, for thermoset polymers, right. The first one was hand layup and spray up. Second one we discussed is basically the we call it filament winding, right, filament winding, and then the pultrusion. Okay. Now, let us discuss few techniques which are used to make polymer matrix composites, but in this case the polymers are thermoplastics, right. Now, the thermoplastics means we can actually heat it little bit to have better bonding, okay. So, that is what you will be seeing here. So, the first technique is film stacking. In the film stacking, what is done here, you can see here there are these pressure plates, and then in between also we have these metallic tin plates which are basically used to pressurize whatever you keep inside. Now, what is there inside? Inside you can see there is thermoplastic films, and this fabric is basically the fiber fabric. So, what is actually done, let me just quickly try to draw it. Okay. So, what is done? So, there will be like fabrics of fibers. So, this is the fiber fabric like this. Okay. So, there will be multiple fiber fabrics like this. and then so these are all fiber fabric, okay, and these fibers could be, as I mentioned earlier, glass fibers, sometimes for high for a high strength application silicon carbide, otherwise glass fiber or Kevlar, okay. And then what is being done here is that in between these two there will be the layers of this kind of thermoplastic films, okay. These are all thermoplastic films on top, okay, at the bottom, they are all actually these thermoplastic films. And then the whole setup, so you can see here, this is actually, that is how, and in between the tin plates. Now, what are the function of these tin plates? To keep them intact, keep them separate, okay. So, and then heat and pressure is being applied in the plate. So, you are applying pressure, at the same time you are applying heating here. Now, heating leads to flowing, or the viscosity goes down then of the this thermoplastic material, and then there will be penetration of the thermoplastic material inside this. So, you can see this, there will be penetration of the thermoplastic material inside the fiber pores. So, the fabrics are basically loosely woven fibers, right. So, in between that those porosities, the plastic goes in, the thermoplastic material goes in, and because of application of temperature and pressure, and then ultimately it gets densified. Once the temperature is removed, the heat is removed, then it gets solidified, and then you get this composite material, which is basically a polymer matrix, thermoplastic polymer matrix, and this kind of fibers will be there, okay. So, that is film stacking. Now, let us go into the next one, is diaphragm forming. Again, the basic method is same, that application of temperature and pressure, okay. So, here also you can see there is a diaphragm, okay, and inside the diaphragm, inside this, so there are two diaphragms actually. Let me quickly try to draw it. So, this two diaphragms, and in between the diaphragms again this setup of alternating layer of film, thermoplastic film, and the fibers, okay, like this, okay, and this will be inside the, this will be inside these two diaphragm films, okay. Like as you can see here, it is being done here, okay, and then it goes to a heating oven. So, it gets, the whole thing gets heated, and then it is kept inside a mold. You can see the mold here, right, okay. Now, in the mold you can see what is, there are two ports, application of pressure. The mold is basically this shape, this wavy shape is the mold, okay. You can see there is a wavy shape, that is the mold, okay. And then we have two these ports, these two ports are there, one is applies pressure. So, because of application of pressure, this diaphragm deforms and goes into the, sticks into the mold. At the same time, whatever air is remaining inside the mold, that gets vacuumed out. So, again the two kinds of pressure being applied, from the inward a vacuum and from outward a pressure, and that leads to deformation of the diaphragm according to this mold, and obviously whatever inside the diaphragm, that is basically these layers of this thermoplastic film and the fibers, that also gets deformed like this, that also take the shapes of these molds, and then ultimately it gets solidified. So, you get a shape like this. So, this diaphragm forming basically is used when you have a complicated shape to be made, then diaphragm forming is used. right. Okay. Now, let us move into the next one, and the last one is the injection molding. Okay, you can see here how it is happening. So, there is this thermoplastic polymer is there, okay, and you see it is being shown here. So, there has to be here there will be a preform, and this preform is getting impregnated or getting infiltrated with this thermoplastic polymer. Okay. So, there is a, you can see there is a ram, or there is basically a piston which basically pushes the thermoplastic material which is in molten state or semi molten state, viscous state, okay, and then it infiltrates here. You can see here how the product comes out. Okay. So, again you can see here that this preform is getting, so the preform has not been shown here, but the preform is getting infiltrated, and then once it gets solidified it comes out. That is the thermoforming or injection molding. So, again in case of thermoplastic matrix composites, I have discussed three techniques, starting with the first one was film stacking, where films of thermoplastic material and tapes or fabric of the fibers gets stacked, and then ultimately you apply heat and pressure to cure it or to solidify it, densify it. The next one was diaphragm forming, again the same thing, but in this case the application is where you have complicated shape, then you use diaphragm forming, and then last one is injection molding in this series. So, with that I will just quickly show you the properties of few polymer matrix composites. So, interesting thing you can see here, if you are obviously using boron fiber as reinforcement, you can see the tensile modulus, tensile strength, compressive strength, all obviously are quite high in case of boron fiber reinforced composites. Obvious reason because of the boron's high strength and modulus. Okay. I mean, you cannot really compare with glass fiber, the values are quite low compared to boron fiber. But again you can see here you can have different kind of different kind of directions or different kind of designs in which way you want to have your fibers. So, unidirectional glass fibers, bidirectional, chopped strand means short fibers. You can use different kind of fiber setups, and you can get different kind of, for same material you can get, for the just varying the orientation and varying the size of the fibers, length of the fibers, you can see you can have a varied range of tensile strength and modulus. Similarly, you can see here Kevlar 29 and Kevlar 49. So, different kind of Kevlars can be used. Kevlar 49 is having higher strength, but Kevlar 29 is having higher fracture strain. Okay. So, what kind of applications you have, what kind of properties you want, based on that you choose your fibers and choose your polymer matrix, and the processes as I mentioned earlier, different processes, and you get your polymer matrix composites. All right. So, finally, I would like to show you some examples. I was talking about sections. You see by pultrusion how these sections are being made. Okay. And similarly, here also you can see these drumsticks made with pultruded Kevlar, aramid fiber core and a thermoplastic injection molded cover. So, you see that two techniques have been used simultaneously, pultrusion and injection molding both. You can, I hope you remember what is this particular technique, filament winding, by which this kind of large pipes, these pipes are used for carrying huge volume of fluid or liquid to a longer distance, and it goes inside the, gets submerged. So, it has to be have enough amount of strength, enough amount of degradation resistance. Okay. So, these pipes are made by made of polymers, and these are generally reinforced with glass. Okay. So, large diameter glass fiber reinforced filament wound cylinder, so filament winding, as I was mentioning earlier, made for water transport. In this case you can see water transport for irrigation purpose in Ecuador. Okay. Not only in Ecuador, everyone is being used. everywhere it is being used. Then some high end applications like blades of engines are made of carbon fiber epoxy composites. Okay. Then this one you can see here the primary structure and several antennas made of carbon fiber polymer matrix composites. This kind of racing bikes, okay, these are actually used of there is application of carbon fiber epoxy composite. So applications are, you can see here all these blades, these are made by polymer matrix composites. Okay. So all are huge applications of PMCs because of their low weight and high specific strength. Yes, for high temperature applications those are not good, you have to go to ceramics then, but otherwise if you need high specific strength and low weight and good fatigue resistance, then PMCs are definitely quite good alternatives. So with that I would like to conclude today's class. Today I have discussed about two techniques of ceramic matrix composite synthesis, and then we talked about application of ceramic matrix composites. Then we went to discuss polymer matrix composites, their basic concepts, classification, processing techniques of thermosets and thermoplasts, and then we discussed about properties and application as well. So with that actually I have discussed so far. I started with basic composites, fundamentals and principles, and then I talked about fibers, different fibers, okay, what are their properties, how they should be synthesized. I talked about several commercial fibers. Then I started talking about the composites in terms of metal matrix composite, ceramic matrix composite and polymer matrix composite, and how they could be synthesized, okay, how they are commercially synthesized, different several techniques I have discussed. So I think I should end here about synthesis part. Now I want to go into the mechanics of composite. So I will start with interfacial phenomenon in composites, especially in MMCs and CMCs, okay, and then I will talk about different mechanical aspects or mechanics of composite materials. With that I would like to thank you all. Goodbye.